In this video, we're going to define vector operations and then do a couple of examples of vector operations. So if you remember, we defined what a column vector was before, but we'll talk about it again. A column vector is an ordered list of numbers. It's written vertically. Typically, it's written vertically. You can write them. You might see them wrote like this with like 3 and 5. That this is an assumed column vector 3, 5. It's just sometimes easier, especially when you're typing it, to type it like this versus typing it like that. Okay. So again, we usually use the lowercase and we bold them, or we use the arrow across the top, or sometimes you might see it with the tilde underneath. But when we're talking about a vector, typically we'll use the bold because it's easier, especially when we're typing. No other reason than that. And of course, a vector has whatever a number of entries, depends on the size or the components. The number of entries is the number of components. Where, as an example, that when I come back up here, my vector 3, 5 has two components, the first component and the second component. First component goes in the first row, second component goes in the second row. So if we want to think about this almost like as a matrix, it is a one column matrix. That's how we talked about a little bit before. So let's give you a couple of more definitions. So what we see mostly is we really see this as R of M, and we mostly see this as like the Euclidean M space. What we've talked about and what we've seen before is R to the 2. So we're talking about the Euclidean 2 space, X and Y. You might see the R of 3, so we're talking about the Euclidean X space if you wanted X, Y, and Z. The C superscript M just means that we're going to talk about complex numbers, and of course 3 and 5 and 7 and negative 22 are all complex numbers, but it has a strictly real part, but you can write any real number as a complex, so just something to think about. A vector can be used in a variety of different ways, so you'll see them in other disciplines. For right now, we're just going to think of a vector as just a list of numbers. So we're not necessarily going to do the graphing part of it, because you may see it, a vector as a graphical interpretation, especially if you're in 2 or 3 space. Right now, we're just going to think of them as sets of numbers. So then we're going to define the vector equality. What vector equality is we have these two vectors and they're equal. We have vector equality if each value in the positions are equal. So as an example, we're going to use this system of linear equations. I can write everything on the left side as the first row of my vector, and everything on the right side of the equal sign as the first row of my vector on the other side. So I know that all of this is position 1, and this would be position 1 on the other side of the vector. So we can write this as a column vector. We can go even further and say, well, wait a minute, can't I write this as x sub 1 with all of its entries for x sub 1? And the answer is yes. So I'd have 1, 0, and 1, and then plus x sub 2, and then the columns in x sub 2, which is the 1, 2, and negative 3, and then the columns in x sub 3. Here's my x sub 3 there. So negative 5, negative 1, and 1. That's a terrible 5. That is a 5. And that we could say that these are going to be 4, 4, and 1. We have those equalities when I do that addition, which gets me to how I'm going to define the vector addition. What vector addition is that I'm going to add the same positions together. And in vector scalar multiplication just means I'm going to multiply one number as a scalar, and it's going to go and multiply that by each one of the entries in the columns of the vector. So as an example, here are my two vectors. If I want to add these two together using the definition of vector addition, if I'm doing u plus v, then this is going to be 2, negative 3, 0, negative 1, plus negative 4, 6, negative 2, and 7. And this is going to be equal to, because of the equality, I can go ahead and do this addition, and so I get -2, 3, -2, and 6. So that is my new vector by adding those two other vectors together. Similarly, -4 times v, my vector v. So this is going to be -4. That was terrible. Let's do this, try this again. So this is going to be equal to -4, and then all my entries in the v vector, which is 2, -3, 0, -1. So this is equal to -8 and +12, 0, and +4. And lastly, I'm going to do this, which is the 2 times u. U is being the +2, the -3, the 0, and the 1, minus 3. And then it would be the -4, 6, -2, and 7. So first I'm going to go ahead and multiply the scalar through. So that's 4, -6, 0, and 2. And then I'm going to go ahead and multiply that -3 through. So that gives me +12, a -18, excuse me, a +6, and a -21. I'm going to go ahead and add each one of the entries correctly. Row, then the 1, 1, in each one, and so that gives me the 16, -24, 6, and -19. And so that is just that addition with some scalar multiplication in there. Okay, so here is the Nyx theorem. It says if I am working with complex, or it could be an R2 or R3 or Rn, it is the set of m additions and scalar multiplications as defined by this. What this is telling me here is that I can add two vectors and my vector will still be within my complex numbers. Now if I'm in reals, so instead of doing Cm and say I'm R2, that when I do vectors with two entries, plus or minus some other vector with two entries, provided they're both real numbers, then my answer will be a real number with two entries, even if the entry is 0. The other thing we get here is this closure, which means that if I multiply my vector by any number that's within the complex, or if I want to look at the smaller set, the real numbers, that its result will also be in the complex vectors or real numbers if I'm in that. I can add them, and it doesn't matter the order in which I add my vectors. So u plus v is v plus u, so that's this one. I also get the associative, the additive with association, so I can add two vectors together first and then get the result and add it to u. Or similarly, I can do the uv and then add it to w. I'm going to get the same answer. We also pick up the 0 vector. So it is the 0 vector. If I add it to another vector and I get the other vector back out, that is the 0 vector. We get the additive inverse. That means if I have, say, the vector 3, 2, and I add to it the additive inverse, which is -3, -2, then I better get the 0 vector out. So that's that one. And I have the scalar multiplication is associative. So say I have my vector is again 3, 2, and I want to do 5 times 7 times my vector 3, 2. I can multiply first these two numbers and get an answer and then multiply that as a scalar. Or I can do this as 5 multiplied by, and do the 21. I'm going to go ahead and multiply 7 in there. So 7 times 2, which is 14. And it will give me the same answer if I would have multiplied the two scalars first and then multiplied it by the vector. If I took one of the scalars, distributed into the vector, and then multiplied it by the other scalar. The other thing we're going to get is the distribution of scalars. So that's what you expect. Say I have my scalars 1 and 3, or my vectors 1 and 3, and my other vector is -1 and 2. Say I'm going to multiply this whole thing by 5. I can do it like that, or I'm going to do it as 5 multiplied by 1 and 3, not 1/3, 1 and 3. and then plus 5 multiplied by negative 1 and 2, and it will give me the same answer, and it'll also still land in complex, or if I'm reals, in reals. The other thing is I can distribute my addition of the scalars, and lastly, of course, I get the 1 times the column vector is going to give me that column vector. All right, so now let's take a look at this first example. I am trying to figure out that when I take 3, multiply it by 1, add 4, multiply it by 2, I get 11. That's true. So let's check that. Let's do 3 multiplied by 1, just check in the first row, plus 4 multiplied by 2. This does indeed give us that 11, so cool. Then I'm going to do 3 multiplied by 2 plus 4 multiplied by 0 gives me the 6. Cool. And then I have negative 3 plus 4x. So here's the only one that's little like, what? Is equal to 17. And what we're asked to do is solve for x. What is the x that's going to have it so that it's a true statement? And this is just a nice, easy linear equation. So you have 4x is equal to 20. This only happens when x is equal to 5. Take a look at another example here. In this example, I'm going to try to find an alpha so that when I multiplied it by that vector 1, 2, negative 1 and add it to 4 times the vector 3, 4, and 2, then I'm going to get negative 1, 0, 4. So I'm going to go ahead and multiply this through, and I have alpha and 2 alpha and negative alpha. Go ahead and multiply my scalar through on my second vector. That's 12, 16, and 8. And then my last vector, I didn't do anything, so negative 1, 0, and 4. What this first row gives me is alpha plus 12 is equal to negative 1. My second row gives me 2 alpha plus 16 is equal to 0. The last one gives me negative alpha plus 8 is equal to 4. So I get different alphas. So I get alpha is equal to negative 13 for the first one. I get alpha is equal to negative 8 for the second one, and I get alpha is equal to 4 for the last one. Now wait a minute, it's the same alpha. It should be the same alpha. So if we take a look at this, it should be the same alpha. Is any of these going to work? And the answer is no, because if I try to put in 4, so 4 plus 12 does not give me negative 1. 2 times 4, which is 8, plus 16 does not give me 0. Negative 4 plus 8, oh, well, it works for the last one. The thing is that it has to be the same alpha. So there is no alpha that is gonna satisfy that vector addition. Let's take a look at our last example here. So with this example, what I know is that I have 2 alpha and alpha plus beta and 3 beta is going to be 5 and 0. So what that gives me is 2 alpha plus beta is equal to 5, and alpha plus 3 beta is equal to 0. And you're thinking, isn't that a system of linear equations? The answer is yes. And so I can solve however I feel like solving for. I think I'm going to solve by elimination. Multiply this by a negative 2. So I end up with 2 alpha plus beta is equal to 5, and my second row, or my second equation, becomes negative 2 alpha minus 6 beta is equal to 5. I'm going to go ahead and add, 0. Man, I don't know where that 5 came from. 0. Then I'm going to go ahead and add these two together. My alphas cancel, and I get negative 5 beta is equal to beta. That means beta is equal, should be, excuse me, it should be 5. And then beta is going to equal negative 1. Wow, okay. So now I'm going to back substitute it in right here because alpha is already set by itself. So alpha plus 3 times negative 1 is equal to 0. That means alpha is equal to positive 3. Man, I want to put 4 there. 3. Okay, so let's check this. Is 2 times 3 and 3 down here. When I add to it my betas, let's see if I can get this one right, -1, and 3 times -1. Ask myself, does this equal 5 and 0? And the answer is yes. So here's my alpha, here's my beta. And basically what ended up happening for me to be able to solve for alpha and beta is I ended up just writing them as 2 linear equations because I know that the entries have to match up. The entry in this first vector, in the first position, times alpha, plus beta times this first position in the second vector has to equal 5. So I ended up with 2 equations, 2 unknowns. That's always nice. That's it. That's it for this video.